important in research activity is to think about our contribution for the society, for the development of the society and the countries. And so my vision is how to pass from the fossil carbon, you can see on the left side, to another system, industrial system with neutral carbon. And in this picture, you can see, of course, some system for oil extraction, but also on the right side, you can see one of the most modern pyrolysis plants, which is in Brazil, a continuous furnace which is producing charcoal for the steel making industry in Brazil. So that means with this plant, I just show you that there exists some technology, industrial technology working on the conversion of biomass wood, which is a very important wood, into charcoal for steel making in these cases, but we can see in the future for biochar and other applications. So one other point which is, I think, important is to take into account the history, the development, the industrial development, and good way, wrong way of this development. And for that, Brazil is very interesting. Why? Because if we look at pyrolysis system, what means pyrolysis today in the world? We have to think about what is it today, what is the situation technologically, what is the situation today. And you can see here the different technology, is it more or less the technology we have here, from here the most simple up to the most developed technology. One thing is interesting, because I use the Brazil case, is the Brazil start with some rustic artisanal kilns, pyrolysis kilns, improve it up to this point here, but after that we have a rupture, we have some final technological problems, we can't solve it, and then they pass through completely different another technology, which is a continuous furnace pyrolysis kiln, which is here. So of course, the development of all these technologies, the choice of these technologies are completely dependent on what? Of the context, of the biomass, the economic, the technology, law or exigence, the performance, but also, and most important of all, the economic viability in the context of different countries. So this situation, we have to take into account the context, the different law, and the economic point of view of each region, depending on the application. So I think it was very interesting. Just some slides to better understand that in Brazil, you have a large development of the technology with, I think, a wrong initial choice of technology. So you have a classical furnace, pyrolysis kiln furnace like this. I don't discuss a lot about that. The idea was to increase at the end, to increase the performance, to increase the productivity, to reduce the economic cost of that, but without taking into account the complete system. Why? Because it was very focused on charcoal production and on the charcoal production without taking into account the co-product pollution or the co-product valorization, etc. And so they increase a lot of development for improving the charcoal production by how? By increasing the size of the furnace, by reducing the cooling step, which is one of the great restriction parts of the technology. For what? To increase also the combustion of the gases, because it was a pollution, without valorization of the process. Also thinking about the condensation of tar or interconnecting some kilns, big kilns, in order to collect the totality of the gas and burn it. All this experience at industrial level doesn't work. I think it's really important to think you have a paper, you have a very nice information, but if you look at the reality in the field or in the plant, you have a very beautiful pictures, but the day, all the day, doesn't work. So it was a very interesting experience and knowledge to have to keep in mind. You know? So at the end, and if you can go back to the biochar, what are the main information we can receive of this historical experience? What is the main challenge for pyrolysis process? The main challenge is summarized in this slide, where we have a biomass here. We need or we want to convert it into some product, co-products, which are here. And how to do that? Through, in our case, pyrolysis step, where we can produce a solid product, which called in our case biochar for the agronomic purpose, and a co-product, which are here. And we want to use a part of the energy content in the co-product in the process in order to be at the energetically to achieve the autonomy from the energy point of view. And the whole co-product here can be used for different applications, and the biochar here can be used in the soil in our case, or in different other applications. We have seen some different opportunities. The first point, the first challenge is how to achieve the energetically autonomy of the system. So that means we need a part of the energy here to be reinjected here to allow the running of the process. This is the first challenge, and it's not so easy sometimes. The second one is, depending on the application, how to control and to locate the quantity which is here compared to the quantity the end product which is here. How we can manage main product and co-products in the process. This is the second challenge. And the first challenge here for the main product is what are the characteristics of the product, how we control it in order to better use it in the final application. So we will have three main challenges in pyrolysis process: energy autonomy of the system, the balance between the main product and the co-product, and the quality and characteristic of the product depending on the final use. For that, my research unit have decided to apply a strategy which is based, it's a common strategy which is based to study the pyrolysis process at different levels. And it's right here, three more one. Why? Because we have three levels at thermogravimetric analysis, which is we use some milligrams, microscale study in order to better understand the convection, the main fundamental scientific knowledge of the convection of the biomass. A laboratory scale, the second one, with some grams, 10 grams, 15 grams, in order to mainly develop and determine the heat and mass balance. The third one is a small plot mass, in order to take into account the upscaling and also to produce some quantity, significant quantity for different applications. And the more one, which is here, is industrial plant. For that, we have partnership with industrial companies, small, bigger companies, in order to connect and apply a support, a technical support, to better interaction between the researcher and the industrial area. In our laboratory, of course, we have some techniques for characterization of the feedstock and the end product, biochar and the co-product, in order to have the main heat and mass balance and to know the properties of the biochar in our APS. Okay, and at the end, we have some trial. We can do some trial in greenhouse or in fields with some partners. And to present some of these things, I decided to show you some results with some projects we have. We have some projects from the European Union, which actually are produced Biochar Africa, Phoenix, some in France, German one, remote, right in the road. So I think about the presentation, last presentation. And in Brazil, we have some also projects with some residue which are babassu for biochar agronomy application and also for fish farming. And in future, I think we can write something about the partnership with India. So I present some characteristic equipment we have. So we have the thermogravmetric analysis with some sample. One thing which is interesting in this equipment is that we can work at different carrier gas, CO2 and steam. We can construct and we construct a specific steam generator in order to study the actuation of biochar or some things like this. And also we can work with elevated pressure. It's an old one we have developed, and so we can work with different conditions. The second equipment and level is at laboratory. We have some reactors, but it's just one of them, where we can work with some grams of biomass, different biomass, mainly in order to determine heat and mass balance of the process, depending on the temperature, depending on residence time, and also the carrier gas, nitrogen, CO2, and we are developing also the connection with steam. And the third one at the pilot scale, we are lucky because we have a platform, an energy platform, a space where we have some small pilot plants in pyrolysis, gasification, with remote engine, we have torrefaction, combustion also, and so we can transfer our knowledge, fundamental knowledge at this level with small pilot plant. We can build some pilot plant. Also, we have competent skills in the construction of small scale pilot plant. And we can work in different conditions also in order mainly to study a little bit the scaling from some grams up to some kilograms, but also to produce different biochar and for agronomic trial at the end, because the logistics is one important point. Another point which may be interesting for you is all these skills of we can do with our partners in the different university, and so we have a strong collaboration with Brazil, and so we develop and place at the university in Brazil some equipment like this pilot plant, which is located at the Federal University of Minas Gerais in Brazil. It's a collaboration, a strong collaboration between France and Brazil, and between CIRAD and this university. And so in this case, we studied the pyrolysis of logs, catalytic logs for steel making industry. And at the end, as I told you, we have a partnership. One of the most important partnerships from CIRAD with industry is with Vallourec company. It's a French company, steel maker company, which is involved, which is located in Brazil, with pyrolysis, industrial continuous pyrolysis transfer of technology from France to Brazil, with the construction of this plant, which name is Carbonization, Bordet and Vallourec, which are the two main partners, industrial partners. We can produce 7,500 tons per year of charcoal continuously, 24 hours per day, and with eucalyptus, and we work on assistance, technical assistance and research activity with this, where we can see here you have the plant, a vertical plant, and we have in the top the wood, which is here, and it's continuously full of wood, and you have pyrolysis on the middle part, and a cooling charcoal at the bottom here, and after that the co-product gas is used, a part is burned in order to maintain the temperature inside the furnace, and the other part is in the combustion chamber for electricity production and heat, and the heat is used for drying. We discussed this morning, and so you have a plant, running plant, and this morning I checked Carboval, Vallourec, Brazil, and I've seen new information in June that there are 3 more plants which have been built in Brazil on this capacity. So now I'd like to speak about one case, which is a Roorkee project, which is called Produce. And this project is, we are involved in the part of biochar production, and the idea is how to, the concept of pyrolysis is how to produce both energy and biochar in order to achieve a neutral CO2 emission, which is a very strong challenge. And so, in this case, we are involved in the project, and the concept is exactly what we are discussing now. That means that we have a pilot plant here of pyrolysis converting a part in a co-product here to burn it for energy use. And the other part, the biochar, which is produces different type of biochar, applied, tested in the greenhouse trial for agronomic test in order to check the performance here, the agronomic performance, and also the capacity, carbon sequestration capacity. And the challenge is to evaluate how to achieve equilibrium between energy use and carbon sequestration for CO2 emission equal 0 or negative. And one another point I think we have to take into account is, as I discussed here, is about the compound interest. What's meant? Because as if you use some biochar here and you can both increase the crop speed, that means I collect more carbon from the CO2 and reducing the natural resources like the water, nutrient with a benefit CO2 reduction. So that means you have also a compound interest maybe, and so the challenge is to change all these things. Here some results about the small scale, on the thermogravimetric scale. We have decided to work with 4 main biomasses or resources, which are rice husk, rice straw, oak wood, because it's used as a residue in France as for the charcoal production, and the digestate, which are here. And here you have the evolution of the biochar heat, depending of the temperature, depending of the gas, carrier gas you use, nitrogen, or if you have CO2, or if you have steam, and you can see that you have some activation or not. The blue curve is under nitrogen, so you have some some nitrogen, and you can see that you have a different reactivity between depending on the biomass. So that means that you have some complex things. Another point is with pressure. We work with 5 bar in order to check, and we have some difference here also. So the idea of that is to increase the charcoal heat, the biochar heat, or modify the chemical structure and surface area. Here we have some mass balance and heat balance. We can see depending on the temperature and the type of biomass. And so we have the distribution of the energy depending on the temperature. We have to choose 3 temperature, 300, which is the start, resist 800, we consider the high temperature, and intermediate temperature. And also we have the analysis of the gas. So we can analyze the gas composition in order to check what is interesting. In our case, at 800 UBC, we produce more hydrogen in relation with other temperature, lower temperature. At the end, one thing which is very interesting and new for me in the project is the key performance indicators. That means that we have some indicators, we can define some indicators about carbon sequestration potential, energy use compared to the initial energy of the biomass. And so you can have some information, data, in order to better choose, select the type of parameters we want depending on these key parameters. We work on the surface area also. After that, all this field is about process. Mass balance, energy balance, of the process, and how we can orientate the choice. But the other part is about the biochar characterization and its effects. And so we work on the surface area with the activated, where we can see that for wood we have elevated surface area up to 1,000 square meter per gram compared to rice husk or rice straw. And we have no surface area, no square meter as in digestate. And it's mainly a micro porosity, nano, because we have a nano size distribution, we can see here, but we can see also the difference between the CO2 activation compared to steam activation, and we have a distribution which is a little bit different. Another point is about the pH and the point of zero chart, which are two parameters in agronomic which are very important, and we measure it. And we are in progress today on the another interesting and important thing is about the water retention. So we have to take into account and be careful about that. Why? Because water retention, it's okay, it's nice for agronomic, but if it's a usable water, otherwise the plant cannot use it. And so here we have some, in another project, we have some results where you can see here the total water retention, but only the green part is how to say, a useful water reserve for plants, and the other part is not. So that is, and here you have different type of biomasses, biochar from different biomass activated or not. So all these parameters are very important. And here you have, it was depending on the concentration of carbon biochar into the soil, how the water retention is changing fully. The next step now for that is to prepare the agronomic trial with the choice of the biochar in relation with all this information we have processed, both processed and biochar characteristic, to produce it through the platform energy we have and the pilot plant we have, and testing, and we have selected more or less, we have defined 3 main regions in France, in Cameroon, because we have some colleagues here, and in Brazil, so we can check in fields the different tests with the same biochar produced at the same place, which is in France. In conclusion, it's one thing it's interesting is we have in past some projects on biochar. It was very new for us, and we developed some projects like Diamant Noir or Babassou in 2016, 2018, and so we started collaboration with to initiate an investigation about that with a very how to say, precise, accurate information about all the parameters we need to take into account. And for that, we developed some tests in Brazil, here with the Federal University of Maranhão. You can see some tests, but without controlling a lot the biochar characterization, production, etc., just to test it. And we create a strong collaboration with our partners, Brazilian partners. And this collaboration, we have some publications, some tests, and this collaboration allowed to increase, because the professor who was involved was after that in France for a postdoc with some agronomic researcher colleagues in order to be trained about the high-level analysis information, and all these things allow us to make some tests and to increase our partnership in this area.
Long live India and France friendship.